session, and Ioan Manolescu is going to kick us off and tell us why planar lattices do not recover from forest fires.
So, thank you. Thank you to the organizers for inviting me to talk here. I also, like already yesterday, I should apologize for a few things before I begin. One is that this is joint work with Demeter Kiss and Vlada Sidoravicius, which is not what is written on the website, but I did ask that they change it. It's just because initially I had another abstract, and then I changed it to this to better fit the conference. I hope it does. So I hope you'll like this. So what I'm going to talk about is actually, in the title we have forest fire, but it's more a model called self-destructive percolation, which I'm going to describe now. It goes like this, and it's all going to be on a planar lattice. We'll take Z2 and we will do site percolation, but you could do kind of any planar lattice, site or bond percolation as you wish. But okay, let's just take this case. So it goes like this. The model has two parameters, P and delta. We start off with a percolation configuration with intensity P. So sites are open and closed, open with probability P independently of each other. And we're going to consider always the subgraph of open vertices. And if I talk about connections, I mean connections in that subgraph. So if P is high enough, we know that there is an infinite cluster. And if there is an infinite cluster, imagine this is just a piece of our lattice, it's actually infinite, we're just going to burn this cluster, meaning we'll just declare it closed. And then we obtain a modified configuration omega bar, say, and now we enhance with the small probability delta, meaning we open vertices again with probability delta independently of each other and of everything that happened before. So I'm usually going to depict this in blue, the ones that we open in this latter stage. So it could be that this is our final configuration. This is the configuration of the self-destructive percolation with parameters P and delta. And we will be interested in whether this one contains a new infinite cluster. So, or an infinite cluster. So just a few observations about the parameters P and delta, what's usually interesting to us. We are interested in P, obviously, big enough so that there's an infinite cluster in the initial picture. Otherwise, it's not very interesting. And delta is usually going to be small. P is going to be just above PC, and delta is going to be considered usually small. Okay, so you can define in this new model a critical parameter delta C of P, which is the delta at which you start observing a new parameter, a new infinite cluster. And this, okay, it's ergodic properties show you that it's independent of basically how you did the first percolation. So it's actually a number. It's not depending on the first sample. Okay, so the question which we're going to study is whether this delta C of P goes to 0 as P goes to PC from above. PC being the parameter at which we start seeing an infinite cluster in the initial picture. So we have something to burn. So let me mention that this model was introduced in 2004 by Vandenberg and Brouwer. And Rob Vandenberg, it's the first time I give the talk in front of him. And so I should also thank him for looking at the draft of this paper when we wrote it. He had very useful remarks. So they introduced this model. And the reason I think for introducing it is also because of its relation to forest fires, which I will describe next. And they conjectured this, that it does go to 0, and study the consequences that this has on forest fires. So afterwards, I kind of came from the outside to this problem. I didn't know much about forest fires. And I think, if I'm not mistaken, at least some people had doubts on whether it actually does tend to 0 or not. And I think, at least I remember Vladas, when we started talking about this, he wasn't entirely convinced that we should prove this or the opposite. So we managed to prove this one first, so we went with this. And yes, I spoiled the surprise, also with the title. The point is that no, it does not delta C of P does not tend to 0 as P tends to PC from above. So this means that there is a delta which, if you take delta small enough, whatever you choose to burn, however thin your cluster is, you're still not going to manage to recreate a cluster. Let me just maybe very briefly explain why it's not obvious, and also why you could hope that the other direction is true. So you could hope the other direction is true because percolation is continuous, so as you approach PC, as P is very slightly supercritical, you get a very thin infinite cluster. So you burn something, obviously, but it's very thin, and maybe just a few open vertices could suffice to bridge whatever gaps this thing left, and to kind of use the finite clusters and percolate, make them percolate. Maybe a not very good reason to think it's not true is that we know quite a little about percolation in the plane, and if you look at it, if 0 is, so you take the origin and wonder if this is going to be in an infinite component. So in the initial picture, as P is greater than PC, even just slightly, it's surrounded by infinitely many paths, which are also in the infinite cluster. So you're going to burn all this. So you need to really be able to, afterwards, the blue vertices that you get are going to need to bridge these gaps to take you to infinity. And maybe you don't get enough enhancement out of this delta to manage to get through these, since there are many of them somehow. Okay, and I'll show that this is actually false, this intuition, in some sense. I'll get back to that. Okay, so this is our theorem, and what I'm going to do is I'm probably going to even try to give you the whole proof of it. But before we do that, I'll talk a bit about its relation to forest fires and what it is. So, forest fires on a... maybe I should also mention another thing about this, is that it's been studied also in other cases, for other lattices, namely for lattices ZD with high dimension D. Basically, it should be true for D greater than 7. It's known for D greater than 19. It's whenever you have the mean field behavior of percolation. It's been studied on non-amenable graphs and on trees. And 2 recent papers showed the opposite of this theorem for in these cases. The 2 papers are by, okay, now I'm going to try to remember. It's 4 authors each paper. It's Daniel Alberg, Gadi Kosma, Vlada Sidoravicius, Hugo Duminil-Copin, and Jakob Dickinson. So, so recent papers that show the opposite in high dimension. So, but you see that this kind of pictures is very 2-dimensional. So what we're going to do now is very, very 2-dimensional. Okay, so what are forest fires? We're going to it's a model that evolves in time. We're going to start off with a lattice which is completely empty, which is our kind of land, and at exponential times, trees will appear at different sites. So time goes by, you see one tree appearing, you see a second, eventually you see quite a few appearing, and these create forests. Forests are just connected components. For instance, here you have this is all a forest. This is isolated because there is no tree here or here to connect it. And when a forest becomes infinite, some accident happens, a forest fire starts, and it instantly burns. And then you continue this process, and the other trees could appear, grow again with the same rule on sites where there were trees before or there weren't, and then they burn again, and so on. So this kind of, the interesting thing with this process would be that well, at the beginning it would be just a coupling of percolation up to time when forest fire start to appear, but then it should stabilize in some sort of a self-organized critical state. That's why a process like this would be interesting. But if if you've studied a bit these kind of things, you realize that it's not completely obvious how to define it. So there are measurability problems which appear, and it's not clear that this process actually exists. So does it? That's a very valid question, and our theorem shows that it basically doesn't. It doesn't. And I'll give you now an intuitive explanation why our theorem should imply that it doesn't exist. So as I said, suppose it does exist, and then for up to time tc, where it's the first time you see infinite forests appearing, there's no infinite forest, no fire, everything is good. And this is just a coupling, an increasing coupling of percolation, which we will also use later. At time pc, this is a well-known fact in 2D percolation, there is no infinite cluster. But any time soon after pc, there is an infinite cluster. Hence, we see already a problem of defining the first infinite cluster that we would like to burn. Okay, but that's not necessarily, if you set it up in mathematical terms, it could make sense. But the only way in which it could make sense is, after TC, since there is an infinite cluster, there should be a fire somewhere. Oh, you could have a fire somewhere here. Otherwise, you'd have a whole regime with infinite clusters. But then again, in this interval here, again, if you don't have any fire, there should be an infinite forest for some time. You can't have that. And you see that the only way for this to exist is to have fires accumulating around TC. Okay? Problem is that our theorem states, more or less, that once you have a fire, at least in this regime here, very close to TC, once you have a fire, you need some positive time to recreate an infinite cluster. Therefore, these two fires here cannot coexist. So this is, I think, a good intuition of why the theorem that we saw earlier implies the non-existence of this process. The way it actually goes is we will prove a crossing estimate that's going to prove our theorem, and that was also shown to imply the non-existence of this process in the original paper of Vandenberg and Brouwer. Okay, so now we'll move to the proof. But I guess I don't know how familiar you are with percolation, so I'll do a very brief recall of what percolation is and what we know about it in the plane. So we know that we have this measure with intensity P. There is a critical parameter that separates the subcritical phase where there is no infinite cluster from the supercritical one where there is an infinite cluster. Both these phases are more or less trivial when you look at them at at large scale. But at PC, there's a lot of interesting phenomena that occur. And one of them is that as you zoom out, you expect to see some non-trivial scaling limit, which is, yeah. So so this is more or less known. It's known on the site percolation on the triangular lattice, but it's not needed in what we do, so it's not based on that. But a very important ingredient in understanding critical percolation is what we call RSW estimates, Russo-Simmer-Welsh estimates. That basically say that if you look at PC, you take a rectangle of side length n by 2n, and you look at the probability that there is a path of open vertices connecting the left side to the right side. This probability should be bounded away from 0 uniformly in n. So this was proved in 1978 by Russo and by Simmer and Welsh, I think for bond percolation, but it's actually now known to be true for any percolation, well, Bernoulli percolation on a regular enough grid. So this we know, and it's going to be essential to our proof. We also know that this doesn't degenerate to 1, and I'm going to explain where that comes from. So imagine you want to cross this rectangle left to right. So you start off from this side, and you discover open vertices, but at some point you're blocked. You can't go any further, you don't reach the other side. Why would you be blocked? Well, you'd be blocked because all the vertices now that you would like to go to are all closed. So you see a sort of path of closed vertices that's blocking you. This is, I will call this a dual path, and you will notice that dual paths are allowed obviously to use the vertical edges, but they're also allowed to use diagonal edges. It's actually, what this is actually a path of closed vertices on what we call the matching graph. So from now on, I'll call this dual path as opposed to these ones that are primal, and I'll denote them by dotted lines. So we also have this estimate for the dual model. We have that dual paths exist with crossings of rectangles, dual crossings of rectangles exist with probabilities that don't degenerate. And when you put these two together, you see that this implies that also these probabilities are bounded away from one uniformly in that. So with this, you can already show a lot of things. You can show that there's a unique critical point, but you can also show the following thing. At the critical point, we're going to look at what we call arm events. Arm events, the most simple one is the one arm event that I've depicted here. It's just the event that 0, or a specific point in your graph, has a path, an open path going to distance n. From these, you can show that this decreases like n to some negative exponent here. And we actually expect that this behaves like n to some negative exponent, but unless we have all the information about the scaling limit, we don't know this. The exponent that's going to be much more interesting to us, it's the 6-arm exponent, which the 6-arm event, which I drew here. So here we're looking for to have 6 paths going from a point or the vicinity of a point to distance n, and these should be 2 primally, so open paths, and 4 dual paths, which are disjoint, 2 on either side of these 2 primal paths. So this we'll call the 6-arm event. And now there's, this is very unlikely to happen. And it's really hard to get this sort of picture. And we can actually show that the probability of this happening is smaller than n to some coefficient, which is very important, is strictly greater than 2. So this is going to be our main ingredient. Maybe I should write it down somewhere. We'll keep it here to remember it. This is general. It's a general thing. It's usually we would, to obtain any kind of specific values on this, we should know the existence of the scaling limit. But the way you obtain this, it's through some, I would say, magical thing that happens. If you just ask for the existence of 5 arms here, this is known to be a universal exponent. So Keston proved this in, I think, 1987. So it's a universal exponent. It's n to the minus 2 if you just ask for 5 arms. And then if you ask for a 6th arm here, this really costs you a little bit more, hence the increased lambda here in the exponent. Okay, so this is what you need to know about percolation. So now let's try to actually look at the proof. If you thought it was technical up to now it's going to get really complicated. So what we're going to try to prove is the following crossing estimate. We're going to take a box like this. This is something like 6n over n. We're going to consider a critical percolation in it. That's supposed to be our initial configuration. And we're just going to erase the left-right crossing, if there is such a crossing. So here we erase all of this. So we're left with basically red points where we don't know what happens, and the white points that are induced by erasing the crossing. And we're now going to color a bit a few points, a proportion delta of them, in blue, for technical reason just in the middle part here, and ask whether there exists a top-bottom crossing. If we manage to show that this doesn't happen, then we manage to show our theorem. I'll explain in a minute why. So this is the crossing estimate that we will look for. Let me very briefly, then you delete every crossing cluster. Actually, you condition that there's a crossing cluster and at least one, and you'll delete all the crossing cluster. So let me explain why this implies the non-existence, the fact that the delta C doesn't go to 0. Okay? So first of all, maybe it shocks you that here I have PC and delta, where actually I should have P greater than PC. But this is an easy thing to see, is that if you look at this dynamical version of the model, you could imagine you let things grow up to TC, you obtain your critical configuration, you burn something here, and then you let it grow another delta. So obviously this is better than letting it grow more, burning it at TC plus delta over 2 and letting it just grow delta, right? You're burning more and you're leaving less time for things to recover. So this is why if you have this, you basically also have the same kind of inequality with P slightly greater than PC and delta slightly smaller. And once this happens, you see what the problem is. With positive probability, even high probability, you're going to see this kind of picture around 0. A circuit enclosing 0 and connected to infinity. So all of this now in the self-destructive percolation, all of this should burn, and then you don't have enough. This delta here is not going to suffice to create a crossing of this annulus. So in particular, you're not going to go to infinity. Okay, so I don't know if you're not convinced. If you try to write it down, you'd see in a minute that it's not at all difficult to see this. And by the way, this sort of crossing estimate that would imply the theorem, this was also various forms of this appeared in the initial papers of Vandenberg and Brouwer. So up to now, I didn't do anything. So what we did now was to prove this, and we're really relying on this kind of picture. So I'm now going to take a complicated percolation cluster that crosses from left to right this box, and I'm going to wonder whether I could, after burning it, cross from top to bottom. So this is our cluster. This is its boundary, which we know is closed if we kind of explore this cluster. The rest, I don't know if it's very visible that the boundary is a bit gray, but the rest in this white area in the middle, all of these pockets, suppose I can roam freely when I try to go from top to bottom. So my only problem is that once I burn this part, I will need to be able to cross the gray and the black part. Right? But I have this delta enhancement that helps me, and one must not forget that we're not enhancing, we're not getting few of these blue points. We're actually getting a proportion delta of them. It's not it's a small proportion, but it's still, you're going to get delta n squared of these points. So since I'm allowing myself to just go around all the white parts anyway, I'm not even going to draw the blue points there. Okay, so we get these blue points. Suppose we get the top-bottom crossing. For instance, this one. I'm going to make a canonical choice and choose the one that uses the least amount of blue points. For instance, this crossing from top to bottom is not the minimal one, because here I use this bridge here when I could have just gone around. So since I want to be economical, I'm just going to go around whenever I can. Use the one with the minimal amount. Okay. So this, I will call this gamma, this path, if it exists. And if gamma exists, I have at least one of these passage points, right? There's a black crossing, I need to cross it, so there is at least one blue point that I'm using. So I'm going to estimate the probability of having a crossing like this by estimating which are the blue points that I'm crossing. I'm going to call these passage points, the points that this path gamma, uniquely defined path gamma, is using. So what's the probability of having this, these points as passage points? And you will notice that if I if I want to estimate the probability that gamma exists, what I could do is just say that it is equal to the sum over all sets x that are not empty of the probability that the set of passage points, so this random set which is around x, is equal to this capital X. So I'm just going to estimate this probability and then show that with the sum in front it tends to 0. Why does it happen? Well, it's because if you take an annulus here, which inside contains blue points, these passage points, but in the annulus itself it doesn't have any. If you look at this picture, you're going to notice that there are sort of 6 arms in the initial configuration, the one with the black and the gray, from the inner side of this annulus to the outer side. So here we kind of see that there's a black one here, and the gray on the top and the gray on the bottom, and here it's almost the same. So you kind of have them here.
Can you repeat what the gray is?
The gray is the boundary of the cluster. So gray is closed in the initial configuration. So we have this 6-arm thing around. If you really look at it in detail, you will notice that actually there's a small trick. There needs to be it could be that one of the arms is actually interrupted somewhere. You see here there was a defect in it. But that's not a big trouble for us. The fact that you have 6 of them comes from the fact that, well, this blue path splits the annulus in 2. On either side of the annulus, you must have a black path that goes to the far, and then you take the boundaries of it. And it's really important that the blue path really splits the annulus in 2 parts and doesn't intersect the gray or the black. This comes from the fact that there are no other passage points on this part of the blue path and on this part of the blue path. Okay, so this shows us that it's really hard to get some of these blue points because 6 arms, if you remember, is very, very unlikely. It's n to the minus 2 plus lambda. So, for instance, this already shows us that there's the chance of crossing from top to bottom by just using one or just a few blue points is 0. I mean, tends to 0, because if you would want to just use one blue point, you would need to have 6 arms from distance 0 to distance n. That costs us this much, and you have n square choices. I'll show you in a minute if it's close to the boundary what happens. But yes, it could be close to the boundary. You would need to take care of these boundary effects. But anyway, that's kind of convincing that you can't use just one of them. But okay, what you could have is you could have a lot of blue points and basically jump from one to another, and all of them having very small 6 arms around them, because you really need to have this annulus, which you need to be far from other blue points to have big 6 arms. These guys don't have big 6 arms around them. And no, that could be a strategy. You could just jump from many, many, many blue points. But then again, on that side, the blue points don't appear frequently, so that could make it difficult. So what we're going to do is we're going to try to quantify that. So on the boundary, what happens is that you will not get 6 arms, as you can see here. You'll get 2 of these going down into the bottom side. So you're losing 6. You're getting 4 arms nevertheless. This one, and the ones on the top. And so you're getting less arms, but also you need them to stay in the half plane. And it turns out that having 3 arms in the half plane has exponent 2. So 4 arms has exponent 2 plus lambda. So both of these, luckily, are bounded the same way. Also, I should mention that, again, because of this crossing probability estimate, the RSW estimate. Yes?
On your picture, we can see 3 long arms.
Which one? This or this?
No, okay, the blue one is not the number.
No. The blue one is the path that, yeah. It's so we're, I'm just, basically the blue is what happens after you enhanced, and I'm just looking at what happened before. The blue is just going to come up at the end, at the very end. So, also one thing that Keston proved, and which is essential to us, and comes from this RSW theory, is that you have some sort of quasi-multiplicativity for these arms. So having arms not from a point, but from a small square of radius, inner radius r, to a big square of radius capital R, also behaves in the same manner. Well, with the ratio here. So this is, well, it's well known and it is important to us. Okay. Okay, so how am I going to estimate the probability that this set of points here is actually this round x? Well, the way I'm going to do is I'm going to grow some blobs starting from each set of points until these blobs meet each other. So for instance, now I just grew a little bit a square ball around this, and this point until they met. These ones also grew at the same speed. And whenever two of these things meet, I'm just going to add an edge, a green edge between these points. This is just a way of somehow encoding these points. So I continue like this, these two met, and so on. What I get here is actually, what I just did is called the Kruskal's algorithm. And what you obtain at the very end here, this green thing, should be the minimal spanning tree of this set of points. So this, I'm going to call the distances of these edges d1, d2, d3, and so on in the order in which they appeared. And my claim is that because of the 6 arms that you see, you put up the formula, you basically get that the probability of having of being one particular set of points is bounded by the product of these d's at the power minus 2 plus lambda. Okay? There's an additional factor here of n to the minus 2 plus lambda. There's an exponential factor c to the k, which comes from combinatorial considerations. And finally, there's this delta to the k here. Delta, I recall, is the probability of actually opening a site. And this comes in because all of this part here was just due to the fact that I needed 6 arms in this initial configuration. Everything was about the initial configuration. In addition to that, I just need that these points are actually blue, that they have been enhanced. If there are k of them, that costs delta to the k. Oh, by the way, k here is the cardinality of this set. Okay, so I'll try to convince you of this formula, or at least where it comes from. It's not so surprising. As you grow these blobs, what you will notice is that if they don't merge, as long as they don't merge, they have 6 arms inside them, right? This guy has 6 arms here because it's a tiny annulus, and there was no other blue point in the annulus. But then also what you have is that in between 2 times at which these merge, for instance here, there are 6 arms in this sort of annulus-like region between when these 3 blobs merge and when they merge with this one. And if you put all of these together and you do your combinatorics right, what you obtain is that, so you obtain all of these dj's, and then at the very end, extending to all of the sets, all the way to the boundary, you obtain this n to the minus 2. Okay. Yep.
Is it a tree in general, or it's
Yeah. It could be a tree. It's just
okay.
like once I drew the picture, I noticed it's not, and I didn't want to redraw the picture. But yes, it could be a tree in general. Okay. Let me just finish the proof now, because we're really close. So the probability of having one specific x is this. Then I'm just going to sum over all the x's. Since I bounded the probability of having one specific x in terms of these distances here, might as well just regroup all the x's with the same distances. So how many sets x with these distances can you find? Well, you have, hope everybody can see, you have n squared choices for placing one initial point. Then you have up to constant. You have about d1, if the first point is at distance d1 from this point, you have about d1 choices for the next. Then d2 choices for the following one, and so on. Okay, I cheated here a bit because for this to know, you should know what this tree actually is and the labels on it. But all this number of labeled trees and so on go into these constants, exponential constants here. So if you do your combinatorics right, this is not going to be a problem. And by the way, doing our combinatorics right was not easy for us. But how we managed. So you get this many sets with these D's. So you're going to want to have here a sum in front over K over D1 up to dk of these many sets, and then of the probability. So the probability, if you recall, was n to the 2 minus lambda, so that gives us a minus lambda here. Then there was d1 to the 2 minus lambda, d2 to the 2 minus lambda, and so on. And now is the magical thing that happens. You know, you can factorize this n, and this is just well, it's the sum over k of the sum over d of d to the 1 minus 1 minus k. Okay. And there was a delta to the k here. So what you see is that because that initial factor was greater than 2, this is greater than 1, so this sum of d to the 1 minus 1 plus lambda is finite. So since these things are summable, as you sum up in d, you're going to get here a finite number to the k. If you put delta small enough to compensate for it, it's just going to be all summable. And with the n to the minus lambda, it actually tends to 0. So here you have the actual computation if you can't read my handwriting, which is very likely. So yeah, so here you have the proof. Before I stop, I just want to make a few observations about this kind of computation. One is that we're not at all of the first to use this kind of computation. It's the typical way of trying to compute moments of cluster sizes in, for instance, of cluster sizes in critical percolation. And indeed, it was used by Keston instead of having the 6-arm exponent, the 1-arm exponent and the 1-arm event to compute moments of the clusters. It was then, what he did is, I think, mostly for k fixed. Demeter also used this to compute exponential moments of cluster sizes and obtain large deviations for the cluster sizes. So it's a technique that kind of existed. It yields different results on whether your exponent here, very different results on whether your exponent here that you consider is greater or smaller than 2. And I was saying that this intuition that we had there about having difficulty crossing these clusters is wrong. The reason is that if you would just consider that, if you wouldn't consider crossing here just the cluster, but just the cluster plus its boundary, but just the cluster, that's very easy to actually cross. The probability of having the probability for a point to be pivotal, meaning to be just necessary to make it blue so that you can cross all the way, is n to the minus 5/4. There are n squared points, so you will find points like that, in principle. If you can't go through in one go, you might need 2 or 3, but in a tight number of steps, you could go through. So it's really, we were very surprised when we found this at first, but the boundary of the cluster, the fact that you just make it fat by just by one more, really changes a lot its geometry. For instance, the pockets of the fattened cluster are much smaller than the pockets of the real cluster. Or if you wish, if you are trying to go from top to bottom, not by a single path of vertices, but by a path of width 2, you're also not going to manage to get through, because a lot of times you're going to want to use these small passage points such as this one, and you're not going to have room. Okay. So this concludes the talk. Thank you.
ideas for dimension 3?
Okay, so I asked myself the question. Obviously, all of this is very two-dimensional. Also, you will notice that even this kind of intuition is false in 3D. Right? I mean, your cluster still leaves a lot of holes for where you could go through to infinity. Nevertheless, there is just one infinite cluster, so you're not going to have two of them coexisting. So I have no idea, but maybe what could be done is, so there's a lot of technology that has been or is being developed for slabs, meaning for just Z2, say, but a few layers of it, but one on top of the other. Even there, I don't know how to do it, although I think now we have tools to really understand well that, that model. But still, I don't know.
Anyone else? In that case, let's take Ioan again. And we'll be back